Lesson 2, we're looking at understanding rational numbers. So page 13. Calvin wants to customize his surfboard so it is wider than the 82 model but narrower than the 92 model. What measurement could be the width of his surfboard? Okay, so wider than 82, narrower than the 92. So you can see that 82 is 22.5 inches wide. The thickness we're not worried about here, so don't have to worry about that number. And then the 92 is 23.25. So we're looking somewhere between 22.5 inches and 23.25 inches. What a possibility could be. So if we think about that, a couple options. One option that would be in between those, in other words, would be 23 inches. The little 2 marks there indicates inches. 1 mark would indicate that it's feet. 22 3/4 was another option that we came up with here. Another option would be 23 1/8 inches. Okay, they didn't ask us to, come up with like 20 different answers here or anything, but just understand these are some options that would work. There would be several others we could come up with as well. So look at the bottom of the page here. It says Lindy's surfboard is 23 1/3 inches wide. Between which 2 surfboard models is her custom surfboard's width? So 23 1/3 would be between which 2 models? So that would end up being between the 92 and the 102 models. And reasoning, it says, how do you know? Looking at the fraction part there, that had a third, the other one had a fourth. So we know that 1/3 is bigger than 1/4. So look at example 1. Juanita is reporting on pitching statistics. Pedro's fastball statistic is 52 out of 80. In other words, 52 out of the 80 pitches he pitched were fastballs. How can Juanita write the fastball statistic in decimal form? So decimal form, if we think about this, 52/80ths, we have a fraction. And the fraction bar indicates division. Remember, in a fraction we have 2 parts. The number on the top is called the numerator. Number on the bottom is called the denominator. And remember, when we go to divide this, n for numerator goes on the inside. Okay. So when we divide that out, 52 divided by 80, 52 needs to go on the inside there. And when we work that out, after the 52 we could put a decimal, we can put some zeros there. That's the same thing as 52 still. And then we just keep going until we come up with a 0 remainder. And so that came out to be 65 hundredths, which you guys may remember, 65 hundredths, that'd be the same thing as 65% if we change it to a percent. They're not asking us to do that, but just as an idea, you could say 65% of his pitches were fastballs. And so notice here, terminating decimal, I'm going to modify a little bit of the book's definition. I'm going to say a terminating decimal is a decimal that ends. I think what the book was meaning is that it ends with a 0 remainder, maybe, but obviously 65 hundredths does not end in 0. It ends in a 5 in my case of looking at it. So I would say, we'll just say terminating decimal, it ends. Okay, we work it out, we get a 0 remainder, it ends. So if we look at the try it, in the next several games, the pitcher threw a total of 384 pitches and used a fastball 240 times. What decimal should Juanita use to update her report? So now it's 240 out of 384. So again, we could write that first as a fraction, 240 out of 384. And then to write it as a decimal, we need to divide it. These numbers are a little bit bigger, so we might be guessing a little bit. So 384 does not go into 24, does not go into 240. So we can put a 0 there in our ones place value position. We're looking now at 384 into 2,400. Well, you might think, if we just look at drop off the last two digits, you might think 3 into 24. 384 is actually closer to 400 than 300 though. So let's think about 4 into 24. How many times does 4 go into 24? 6 times, good. So let's try 6 and see what happens here. Okay, so 6 times 4 is 24. 6 times 8 is 48, plus 2 is 50. 6 times 3 is 18, plus 5 is 23. And that looks good, especially they've already got 2304 on the line there. So that's even more assurance that we did that correctly. Okay, and then at that point we can go to subtract this. In order to subtract, we're going to have to do some borrowing here. Change the 4 to a 3, makes that a 10. We borrow, makes that a 9, makes that a 10. And then you subtract. They actually already did the subtracting, but we can verify, I guess, that they did it correctly. Bring down the 0. So now we're looking at 384 into 960. Again, 384 closer to 400. So we might think about 4 into 9 would go how many times? Twice. Okay, so let's try 2 times here maybe, if I can get this to work. Okay, 384 times 2 is 768, so that looks good. And then again, we have to do some borrowing in order to subtract. Borrowing again. So 192 left. Again, verify that's less than the number you're dividing by. That's less than 384, so we should be in good shape. And then up top, what number are we going to be bringing down? A 0. Okay, remember we can add zeros to our decimal numbers, doesn't change them. And then bring the 0 down. 384 into 1,920. So 4 into 19 is kind of what I'm thinking about as an idea. 4 into 19 would go 4 times, okay? No guarantees here. Notice how, see how they've got minus 1920 there? With the minus 1920, if I do 4 times 4 is what? 16. That's going to end in a 6. Theirs ends in a 0. So I'm going to guess that my number's not right. And let's try 5. Okay, again, the guessing, like we talked about, is not a guarantee. Generally, we'll be within 1, and there it is. 5 actually works for that one. So 625 thousandths. In other words, moving the decimal 2 spots, basically it's saying 62.5% of the time they threw fastballs. Example 2. They want us to write rational numbers in decimal form if we have repeating decimals. So a class votes whether to change their school mascot. How can you express the number of students in favor of a new mascot in decimal form? So 5 out of 18 voted to change the mascot. So we do 5 divided by 18. What happens is we subtract, we get 14. We bring down the 0. We subtract, we get 14. We bring down the 0. We subtract, we get 14. When we can keep going. And this is what's called a repeating decimal. So a repeating decimal is when it repeats the same digit or block of digits without end. In this case, just the 7 is repeating. And so what we do, since just the 7 is repeating, if you'll notice down below, we put a bar above the 7. The bar above the 7 shows us that that 7 is the only number that's repeating. Okay. Just some other examples for you guys just to mention here. If we have 0.333 and so on, that would be 0.3 repeating. Since the 3 keeps going, we can just put a bar over the 3. If we have 0.2488 and so on, just the 8's repeating, so we just put the bar above the 8. One more example, I guess, here, just for variety. We could have like 0.2525 and so on. In that case, both the 2 and the 5 are repeating, so we would put the bar above both of those numbers. So if we look on the try it, they're asking for the decimal forms of these and whether they repeat or terminate. So that's just dividing it out. So 100 divided by 3, 3 doesn't go into 1, 3 goes into 10. 3 times, okay. 3 goes into 10, okay. Now, I'd like to just say we have 1/3 and then just be done. It does say talking about decimal forms here, so we do need to go ahead and put a decimal point and then add some zeros back there. 3 goes into 10, 3 times, okay. And if you want to go one step further, 3 goes into 10, 3 times, okay. It's the same repeating pattern, so if we were writing that in a repeating form, we would just put the bar over the 3 that's after the decimal. You never put a bar before the decimal point, okay? So that would be then repeating, so that repeats, okay? If we did 100 divided by 5, 5 goes into 10, 2 times, 5 goes into 0, 0 times, okay? And that ends, so that terminates, we could say. Okay? And then the last one, we've got 100 divided by 6. So 6 doesn't go into 1, 6 into 10. 1 time. 6 into 40 would go 6 times, which is 36. And we're going to have to keep going on this one. 6 into 40, 6 times. Okay, and that's just going to repeat as well. So that would be, if you wrote it out after the decimal, would be 0.6 repeating. And then so that we could say repeats itself. Example 3 asks us whether each of these is a rational number. They have not, that I've seen, given us any kind of definitions or anything. So before we do this, let's talk about what rational numbers are. So, definition of rational number, it's something that can be written as a fraction with 2 integers. Well, now we got another definition. Integers, we have to know what that means then. Integers, it's a set of numbers that includes negative numbers, 0, and positive numbers. With integers, though, there are no decimals or fractions on the integers. Okay, so move down my definition of integers here, maybe. Oh, it grouped them together. Here's going to be some examples then of rational numbers. Okay. Examples of rational numbers. One example of a rational number would be 3/5. Okay, that is literally a fraction with two integers. Oh, by the way, the word rational, if you look at the word rational, the first part of the word is ratio. That's a way that maybe can help you remember how a rational number works. Ratio, remember we talked about, it's a fraction that compares two things. That's a way maybe can help you remember that. -8 would actually be a rational number because we could write it as -8 over 1. Okay. If you have a decimal like this, decimals can be rational numbers because that would be like 7/10 as a fraction, 7 over 10. Okay. A repeating decimal, we'll get more into this next year. Repeating decimals can be written as fractions. So like if I have 0.4 repeating, that's the same as 4/9 as a fraction. And again, we'll learn about that next year more so. Square root of 9. Square root, what number times itself equals 9? That would be 3, which we could write as 3 over 1. Okay, so you look at this and you might then say, well, that's rational numbers. It seems like pretty much just everything's a rational number. And that's actually not true. There are things called irrational numbers as well. All right, so again, before we think that everything's rational, there are things called irrational numbers as well. So irrational numbers are things that have non-terminating, non-repeating decimals. Decimals keep going, they don't repeat themselves. So for example, if they told me we had 0.13782 ... if it's got dots and there's not a pattern, my only assumption is that that keeps going and doesn't repeat itself. Okay? Square root of 7, if we do a square root of something that it's not a perfect square, doesn't come out evenly, that is going to be irrational as well. Okay? We can't get a number times itself to get 7, doesn't come out very well. Pi, you may have heard of before, remember that. It's about 3.14, but actually the decimals keep going and don't repeat. Okay? So it seems then, a lot more things would seem then to be rational than irrational, but there are things that are irrational numbers as well. So now we go back to example 3, whether these are rational numbers. You can see on example 3, part A, that decimal ends, so that's rational. We could write it -6 and 382 over 1,000. We could change it then to an improper fraction if we wanted to technically have our definition. But again, basically, if the decimal ends, if we don't have a decimal that keeps going and doesn't repeat itself, then it's going to be rational. Okay. Part B, at the end there, it is repeating, so that would be rational as well. C keeps going. We don't see a pattern there necessarily at all, so that would be not a rational number, or we could say an irrational number. Okay? So if you look at the try it, they're asking on those two whether they're rational or not. So the first one, -0.3 repeating, with it being a repeating number, would that be rational? Yes. Okay. Repeating is rational. They both start with an R. That's a good way to remember maybe. And then the next one, 3.14141444144444. I don't know. I lost track. Anyway, that one, I don't know if we specifically talked about. You may have an idea in your mind. That actually, it's a pattern, but it's not exactly repeating the same thing every time. It's not the exact same every time. And so that would not be a rational number. That would be irrational. We can't write that as a fraction with two integers.